part of the work and energy in dynamics also has relationship to the springs, and we haven't talked about the force of the spring. So this one is called Hooke's law, and we're going to be talking about how is the force acting on the object when you attach it to the spring and stretch or compress. So the Hooke's law has this formula. The force of the spring, the negative sign means it's always opposing to what you're doing to the spring. So if you're stretching the spring, it pulls you back in the opposite direction. If you're compressing the string, it pushes you back away from compressing the string. So the force that is determined by the force of spring is equal to K and change of the distance of U by how much you stretch or compress. And K is the spring constant, and spring constant is determined by the manufacturer. So when the spring is made, they test it and they will say, okay, this spring constant for this spring is such and such number. And so the spring constant K has measurements. It is newtons per meter, and it has the definition as well. So let's say if the spring constant is 3, that means when you stretch the spring by 1 meter, the force that is, so if you stretch the spring, the force is going to be acting back to put it in the equilibrium position, and that force is going to be 3 newtons. So it's 3 newtons per meter. So that's what the definition of the spring constant means. And also the when you stretch the spring and you attach the block, like you see on the picture on the right, so if you attach the block to the spring, then when you stretch the spring is given some potential energy. And potential energy, it means it is able to do work. So if that spring is going back to equilibrium, the block is going to have some kinetic energy. Where does the block get kinetic energy? Because it's going to be moving with some velocity. Well, it gets its kinetic energy from the energy that you gave to the spring. So when you stretch the spring, you give energy to the spring, and the spring is able to do the work on the block and accelerate it toward the equilibrium position where the equilibrium of the spring would be. So these two formulas, one is potential energy, and it's 1/2 kx squared. K is the constant, spring constant. X is by how much you stretch the spring or compress the string. This one is measured in joules because it is potential energy. So this is in joules. And this one is force. So this is just the force by how much force is acting when you compress or stretch the spring. Two different things, two different formulas. You just have to remember which one to use and think which one to use where. Sometimes we use this formula so much that we forget about the other formula also exists. So let's look at some examples where we're going to be applying our Hooke's law formula. So here's the first problem. A block with a mass of 5 kg is attached to a horizontal spring with a spring constant of 400 newtons per meter. The surface of the block rests upon is frictionless. If the block is pulled out to the distance of 0.05 meters and released, find the speed of the block at its equilibrium, find the speed of the block at 0.025 meters from the equilibrium, and repeat the experiment if the friction is also given and the coefficient of friction is 0.15. Doing it the way I do usually in the classroom because I have limited space. So I'm gonna underline everything that is given. The mass is given, so I always start my problem with what's given. The spring constant is given 400 newtons per meter. That means if you stretch a spring by a meter, it will act with 400 newtons force to put it back in equilibrium. Then we have the stretch at first is 0.05 meters. The stretch, the second one, is 0.025 meters. And coefficient of friction is given for the last part. So at first we're going to do A. So let's do A in some color. Let's do it in yellow. Find the speed of the block at its equilibrium. So when I stretch the spring from equilibrium, so here I have my block. And let's say right here would be the equilibrium, x sub 0. When I stretch the block of the spring with the block from the equilibrium delta x, and this delta x is 0.05 meters. Then I give the block some block of mass. I give the block potential energy. So the spring potential energy, I'm going to look at conservation of energy. So I'm going to look at energy before. So initially I have, so the energy before is going to be equal to the energy after, because the total mechanical energy is going to be conserved in this case. So the momentum, I am going to use momentum before and after when we do momentum, next section that we're learning. So here I have, when I stretch the spring, the block is not moving, it doesn't have kinetic energy, but it has potential energy. So the potential energy the spring has, initial, will go into the kinetic energy of the block when it passes through equilibrium. So that's kinetic energy final of the block. So the potential energy of the spring is 1/2 kx squared, and that will go into the kinetic energy of the block, which is 1/2 m velocity of the block final when it goes through equilibrium. So I see 1/2 from both sides. I'm going to cancel 1/2. So the maximum stretch in this case was 0.05. So K is 400. Stretch was 0.05 squared. And the mass of the block is 5 kilogram. And I have final velocity squared. So from here I find that my final velocity is equal to 0.45 meters per second. So that is the velocity of the block when it passes over equilibrium. So now let's look at the B part. Find the speed when it is 0.025 meters away from the equilibrium. So now I'm looking at this. So let's say I just redrew the picture so it's easier to see. So let's say initial stretch was 0.05 meters. And now the block is not back to where it should be in equilibrium. It is still away from the equilibrium. So it is still some distance away. So that means there's still some distance 0.025 meters away. So when the block is in equilibrium, then all the potential energy of the spring went to the block. Kinetic energy, block's kinetic energy. But the block is not back to equilibrium. So that means at this position, I have potential energy of the spring and I have kinetic energy of the block. So let's try to rewrite this part. So I'm going to do the same conservation of energy. So the before energy is going to be equal to the after energy. And my initial energy, when I stretch the block is not moving, nothing is moving. The only energy I have is the potential energy of the spring. So I have started with the potential energy of the spring. And that potential energy at this new position is going to be still equal to some potential energy. Maybe potential energy initial, I'm going to call it maximum in this case because it's the maximum stretch. And this one, still potential energy of the spring, I'm going to call it SP for spring, and plus the kinetic energy of the block, I'm going to call it B. Now I'm going to plug in what I know. So I have 1/2, and potential energy of the spring maximum is KX maximum squared equals to 1/2 kx, and then this x is the new x, is the one that 0.025 away from equilibrium squared, and plus 1/2 the kinetic energy of the block mv squared. Now I see that every single term in this equation, so I have one term, two terms, three terms, every single one of them has 1/2, so I can times them all by 2 or just cancel 1/2. And after this I'm going to move kx to the other side. So I have k, I'm going to take it out. I have squared maximum minus x squared and equals to mv squared. So from here, I see that the velocity of the block when it is 0.025 meters away from the equilibrium is equal to k x maximum squared minus x squared and divided by the mass. If I plug in all my numbers, I will get that the velocity at this moment 0.025 meters away from the equilibrium is equal to 0.39 meters per second. So that's my answer for B part. And for C, they ask you to repeat the A, but now there is friction. So I'm going to erase this and redo the whole problem if there is friction. So for our C part, we started with maximum stretch at X max. We need friction. For friction, I need the normal force. So I'm going to draw the forces that are acting on the block. I have mg, and I have the normal force. And I also have the force of the spring. So this is F of the spring, which is equal to negative kx. I don't care about the force of the spring at this case. What I do care is the normal force. And in this case, the normal force is equal to mg. They cancel each other. So the force of friction, let's call it the lowercase f. And that is mu times n, which is mg. So I have this. Now, let's talk about the energy in this case. So I need again before and after. So I'm going to have before energy should be equal to the energy after for conservation of energy. My before energy, when I stretch the spring with the block, I have the potential energy of the spring again, maximum. I'm going to call it this way. And then after, this time, not all the potential energy of the spring will go into the block's kinetic energy by the time it reaches equilibrium. So it's like a tax guy. Your friction is like a tax guy. So you earn some money and then they say, wait a minute, give us some before you go spend the rest, right? So the same is in this case. Not all the potential energy of the spring is going to go to the kinetic energy of the block because at first you have to pay a tax. You will have to pay to the work of friction. So the friction is going to steal some work. Not all of the energy is going to go into the block. Some of it is going to be given away to the friction. And then the rest of it is going to go to the kinetic energy of the block maximum at equilibrium. So that block is going to reach its maximum velocity. It's going to be a different maximum velocity because now not all the potential energy of the spring is going to go to the kinetic energy of the block. So let's write everything that is given now. So we have potential energy of the spring, which is 1/2 kx maximum squared minus the work done by the friction. That's the force times the distance cosine theta and angle of the friction. So here is your friction. So here is going to be my friction, and the friction is parallel to the motion of parallel to the distance traveled. So cosine is 0 degrees, and cosine of 0 is 1. So I don't have to write that part. So what I'm going to have here is the force of friction times the distance, and the distance in this case is x max. So it's the force times the distance cosine theta equals to, the rest is going to be equal to kinetic energy of the block, 1/2 mv squared, and it's a new maximum velocity. Now I'm going to plug in all my numbers. So I have, let's do times them all by 2 as well so we don't have to have a fraction. So times the first one by 2, I get kx squared max minus the force of friction, mu mg. Then I have x max. I have to times it by every single one of them by 2, so there's 2 appears right there. And then if I times the last term by 2, fraction goes away, and I have mv max squared. So now the velocity maximum, if I plug in all the numbers, so this one is 0.05, this one is another 0.05, the mass is 5 kilogram, g is 10, mu is given 0.15, and k is 400, and mass again 5. So if I plug in all my numbers, I get 0.23 meters per second in this case. So you have the lowest velocity in this case because the friction is involved and takes away some of the energy. Here's another question. 50 kilograms circus Acrobat drops from a height of 2 meters straight down onto a straight board with a force constant of, so we have the spring has the force constant of 8,000 newtons per meter. By what maximum distance does she compress the spring? As always, I'm gonna underline everything that is given. So she is 2 meters above the ground. So the distance that she is above the ground is 2 meters. So that's the height. Down is she's 50 kilogram, and the constant is 8,000 newtons per meter. So when she's above the board, before she lands on that springboard, she has potential energy. So I'm gonna say the system has potential energy initial, or I can call it the maximum potential energy. So before she lands, I will have to start with potential energy that she has. Potential energy, gravitational, and maximum. And after all this energy is going to be conserved, she will have some velocity right before she hits the board. So I could calculate her maximum velocity, but I don't care about this velocity because what happens is potential energy was going to go to the kinetic energy, and that kinetic energy is going to go to the spring energy when you compress the spring. So I'm going to say all that is going to go after to the potential energy of the spring. I could also say it this way. I could say that all this is going to go into kinetic energy maximum of her. So her kinetic energy maximum. I could find her kinetic energy, and that will go to the potential energy of this spring. So all I need to look is at the gravitational potential energy equals to the potential energy of the spring. So what I have is mgh is going to be equal to 1/2 kx squared. Her mass is 50, g is 10, h is 2, equals to 1/2. K is 8,000 and x squared. So x is equal to 0.5 meters or 50 centimeters. So all the questions that I do for you here explained through the videos, you also have all of them in your online lessons under. So a lot of them are solved just solution, step-by-step solution. So you see a step-by-step folder where you can find all these videos as well. So here's one more question. The horizontal surface on which the block slides is frictionless. The speed of the block before it touches the spring is 6 meters per second. How fast is the block moving when at the instant when the spring has been compressed by 15 centimeters and the spring constant is given 2,000 newtons per meter? And what is the maximum possible compression of the spring? So here I have my drawing, so you will be able to see my work. So I see the block is moving at the velocity. By the time it reaches the spring, it has 6 meters per second, so it has kinetic energy. So when I look at the problem, right before the block touches the spring, the system has before energy. So this is going to be before energy. And my before energy is the kinetic energy of the block. So I have kinetic energy of the block. And then all this kinetic energy is going to go into at the yellow mark, which is only 15 centimeters compression, not the full compression yet. I have the potential energy of the spring, some potential energy of the spring, not maximum potential energy of the spring. And I still have some kinetic energy of the block. And I'm going to call the first one maximum because this is the maximum velocity of the block, 6 meters per second. And then there's still some energy of the block afterwards. So this is the after. And kinetic energy of maximum is 1/2 the mass and velocity maximum squared. So this is the velocity maximum, 6 meters per second. Then potential energy of the spring is equal to 1/2 K, and X they give you by how much it's compressed, squared. And then I still have the velocity of the block, which is 1/2 mv squared. And they ask you how fast is the block moving, so they ask you for that velocity. They all have 1/2, so I'm going to times them all by 2. And I have mv maximum squared. I'm going to move kx to the other side, to the left side, minus kx squared is equal to mv squared. Now, if I solve for v, the velocity at the position x when it's compressed by 15 centimeters is going to be equal to, so the mass is 2 kilogram. Initial velocity squared is 6. You can see that it is 2 kilogram in the picture. Squared minus k, which is 2000, and x is compression point 15 squared, 15 centimeters, and divide by the mass, which is 2. So I get the velocity is equal to 367 meters per second. So I got this number. And then for B part, I need to know maximum compression. So for B, to find maximum compression, I'm going to say that all the B4 is going to go into all the kinetic energy after, or potential energy of the spring after. So now I have all the kinetic energy of the block B4 maximum is going to go to the potential energy of the spring maximum. So I have 1/2 mv maximum squared is equal to 1/2 k maximum compression squared. And so from here I see that x is equal to 0.19 meters or 19 centimeters if I plug in all my numbers. Here's one more question. 0.5 kilogram block rests on the horizontal frictionless surface. The block is pressed back against the spring, having a constant of 625 newtons per meter constant, compressing the spring by 10 centimeters at point A. Then the block is released. Find the maximum distance d the block travels up the frictionless incline 30 degrees with the horizontal. How fast is the block moving when it is halfway to its maximum height? So let's write each point A, B, and C, what kind of energies we have at each point. So at point A, I have potential energy of the spring maximum. So this is potential energy of the spring maximum. Then at point B, at 1/2 the height of the maximum distance it travels. So at point B, I have the potential gravitational energy of the block because it's a certain height, and I have kinetic energy of the block. And at point C, at the maximum height, I have potential energy gravitational maximum, and I have kinetic energy well, actually I don't have kinetic energy, so the kinetic energy is going to be gone because the block is going to stop. So let's look at conservation of energy now. So at point A, I have potential energy of the spring maximum. Then at point B, I have potential gravitational plus kinetic energy, and the spring loses its energy because it gives all the there is going to be maximum kinetic energy of the block before it starts going up the hill or up the incline, but I don't have to worry about that one. They don't ask me about maximum velocity of the block as the spring is released. And then at point C, I have maximum gravitational. Now I'm gonna plug in the formula for each of the energies. So now I have 1/2 kinetic, 1/2 kx squared maximum equals to, at point B, I have potential energy mg, but h is, it's 1/2 of the maximum, so 1/2 of the maximum, and height. And then at B, I also have a velocity because the block is still moving up. And then at C, I have only potential gravitational energy, which is mg, and h maximum. Next one, I'm going to look at what is given and then plug it in into my formula. So the mass of the block is given, the spring constant is given, and the angle is given. And that's about it. So what do I need? I have K. I also have the compression, maximum compression. So I have everything that is needed for this part. The mass is given, g is given, height I'm looking for, and velocity b, I cannot find velocity at b yet. So I'm not gonna look at that part yet. Let's do the maximum height. So the mass is given, I can find this height over here. So I'm gonna say kx max squared is equal to, I'm gonna multiply both sides of the green parts by 2, and I have 2mgh max. So from here, I can find the maximum height. That is equal to, and I have the maximum height is equal to 0.625 meters. And if I look at the triangle, the maximum distance to travel along the incline, so this distance, and this one is theta, 30 degrees, they give you 30 degrees angle, and this is the maximum height. You have sine theta is equal to h over d, then d is equal to h maximum over sine theta, and that will give you 0.625 divided by sine of 30, and that gives me 1.25 meters. So all this was part A. Now for B part, I have to find the velocity of the block when it is halfway through. So what I'm going to look is at the yellow part. So I have this and I have this, and I'm looking for the velocity of the block. So I'm going to simplify my equation now. At first, I'm going to times both sides of this equation in yellow by 2 to get rid of the fraction. If I times both sides of this equation by 2, 1/2, 1/2, and 1/2 is going to be cancelled. And I have wherever is written here, and I have to solve it for the velocity at point B. And so I get 2.5 meters per second. And when I say my h right here, that was 1/2 of h maximum, so I had to plug in h maximum into my equation. So when I plug in all the numbers that are given in the problem, then and the numbers are, I have K is 625, mass is 0.5, and that's about, and the distance is 0.1 squared. So that gives me velocity of 2.5 meters per second at point B. So this is it for our energy and work video number 4 lesson. And we went over the spring energy and the spring forces, the Hooke's law, and a few problems how to solve. I'm going to do more problems related to the Hooke's law and spring energy in the following videos. And also in the following videos, the links are going to be in the description. You will see more videos on energies. There's might be 2 more videos after this one.